or Fab Lab in Bohol, was established in May 2014 as part of a global network of local fabrication laboratories that nurture ideas. A space for co-creating, innovating, learning, and sharing knowledge. To foster local economic growth and community advancement through creative solutions, DTI, through FabLab, has identified 4 areas of development: innovation, MSME assistance, capacity development, and collaboration and partnership.
A Fab Lab is an interdisciplinary space that promotes innovation through the use of digital fabrication tools. It's a modern facility that allows our SMEs to do prototyping. For the last 1.5 years, we have been teaching them digital fabrication skills, which are very much in demand in the world market.
For us, it really would support creation of maybe high-end products and development of new enterprises that are technology-based.
This one will be the common service facility of industrial designing in the province of Bohol. There are even seminars, conferences, workshops conducted here so that Fab Lab enthusiasts and other designers would use the facility.
The concept was introduced to us by our Japanese volunteer, Mr. Yutaka Tokushima. He noticed in the course of his product development activities here, he noticed that a lot of the problems in prototyping could be solved if we had the right equipment to do it.
We've catered SMEs to really expand their market into the tourism sector.
We have all these industries, and ang thing is they're all kalat-kalat, and they're all spread out. And I think having this Fab Lab would bring them all together.
True to its thrust in catalyzing innovation, DTI, through Fab Lab and its local partners, has initiated key programs, projects, and unique initiatives in the areas of waste upcycling and material engineering. Prefabricated shelter designs, startup support and development, equipment development, and knowledge hubs for new innovations and technology-based solutions.
The timing man nga ning abot ang tagahapon nga mo naa sila ihatag. So mao to nga nalipay may kay ni aning abot ning kiwi house nga mo gi karon na mo serve as daycare center.
Key MSME assistance initiatives such as product design, product development, productivity enhancement, and marketing solutions have been significant drivers in the improvement of grassroots entrepreneurs and homegrown innovators.
We do some native bags, placemats, wallets, curtains, and lately I do trophies and medals for the triathlon with the use of Fab Lab facilities.
The problem that artisans face here in Bohol are really the same challenges that any small business faces across the world, and that's how to get your product in front of your customer. So we developed a kiosk called the Made in Bohol Kiosk and sought to have it located in the luxury hotels where the tourists were staying.
Pag butang nimo aning dating molder na mo, pag butang nimo, patigasin pa. In pila ka minuto pa usa pa nimo tanggal. Broken ni siya, gasigi pa mighimo ana, kasi mo iwa pa mahuman ng uban, pwede na mo siya itaktak kay gahi na. Wala na kay minuto o oras nga magamit aron pa mo gahi aron maputos. Kani siya diretso na. Mas daghan, mas napasayon, mas niangay ang among customer. So dako kay natabang ang Fab Lab sa mua.
Ang improved na siya nga sticker namo sa bagol na siya kay ang among canister is naka-embed man siya sa taklob. So kani siya sa bagol na siya. Kaya before, mag-cut out man ni, kami mag-print, ordinary lang nga band paper ang gigamit, kami na mag-cut. So karon nga na-adirig, introduce siya sa DTI. So nag-try ko nga magpa-print. Ganahan na sila. Sila, oy, nindot lagi mag-packaging. O, kaan lagi ni, klaro kaayo. Oy, sinaw na lagi ni. Kanang nga na siya na mga feedback ngayon, ana.
When Fab Lab came, we had this partnership with them para maging competitive din tayo sa market. So, eto po yung isa sa mga FabLab. This is our newest package na po sa mga placemats po namin. Madami po kaming nabenta na po nito, and we're very thankful to FabLab. Tumaas po yung income ng kooperatiba. Kasi may added value po yung mga produkto na namin.
To fuel global industry competitiveness, local entrepreneurs, students, and innovators are brought together to equip them with 21st century skills and tools through digital fabrication, technology trainings, and livelihood trainings and seminars.
It's for everyone. I would say a lot of people really likes to make almost anything. Doon, merong bata, merong matanda, merong zero knowledge, merong may medyo alam na. When you see people came in and then yung parang may sparkly eyes sila dito, when they came like, oh, pwede pala to siya, pwede palang gumawa ng ganito.
The Department of Trade and Industry conduct workshops and trainings for those because they want also to help those young local people here in the country. Because they want also to enhance their skills, improve their skills by the use of the FabLab Bohol. So, because FabLab Bohol, the concept of FabLab Bohol is to innovate and to create inventions by the use of digital fabrication.
This FabLab should be duplicated in other regions because this is a good avenue for developing the skills of designing on the students' part so that we could be ready or we could be at par with other countries in designing.
It's actually, for me, it's like a gold mine. A gold mine for innovators because everything are there na. Laser cutter, shop boot, 3D printers, Arduinos, mga testers na ito. As of now, there are so many micro and kitchen-based enterprises that would really need to improve or upgrade their technologies, their equipment. And that's why we are supporting FabLab because it is our vision that this facility could help those in making those customized equipment.
The FabLab affords its users access to global knowledge through regular educational tours and access to the international FabLab network. Local and other Philippine startup communities, enterprises, designers, and enthusiasts are encouraged to collaborate amongst themselves to expand and strengthen their niche in various market networks.
ボホールではファブラボを使って、必要なものを必要な分だけ作るというイノベーションが徐々に現地の人の手を使って生まれてきています。これは、他の国のファブラボでは見られないようなボホール独自のイノベーションと言えるようなものです。
The laboratory boasts of an array of digital fabrication equipment which include a laser cutter, 3D printers, a digital embroidery machine, a print and cut machine, a CNC milling machine, and an automated wood milling machine. FabLab Bohol also houses a pool of passionate in-house designers and highly skilled staff who can assist in 2D and 3D design, skills training, modeling, and production.
Our task here is to assist those researchers, innovators. So what we did here is not for us to create their idea, but them to create by themselves, and we will assist.
In partnership with the DTI, Bohol Island State University, DOST, and the Japan International Cooperation Agency, or JICA, and the local community of enterprises, FabLab stands at the center of innovation in Bohol.
We are very thankful of the help of the DTI. They can give you a very good service and you really can come up with a very good product.
Kasi we want the Bigan Weavers to really soar high, and our partnership with FabLab will bring us to that level. So thank you po FabLab and DTI.
I encourage everyone, especially taga Bohol, mga students, mga innovators, or mga out-of-school youths, try mo sa FabLab. If ever wala pa niyo nakit ang imuhang gusto himuon no. Basin naa mo kita sa Fab Lab.
It's a great privilege bitaw sa ato kay nga natagan tag chance nga matagan og Fab Lab diri nga makita mo ma-amaze jud mo sa mga magama ni Fab Lab matabang niya para nato sa Bohol.
If you wanted to build a robot or night vision goggles or just something that lights in the dark, this is the place for you.
I would like to invite everyone to come at Fab Lab and let's play with these machines and let's work that idea out.
きっと皆さんのアイデアと、ボホールが持っているイノベーションがそのコラボレーションすることによってさらにもっと面白いものになると思います。ぜひ皆さんボホールにお越しください。
Fab Lab Bohol, a place where ideas turn into reality. Ideas that can improve lives, not just for Boholanos, but for all Filipinos.
Mga kababayan, ang pambansang awit ng Pilipinas.
Kayang magiliw, ewas ang sinakalan, alam ng puso, sa gitid mo'y buhay. Lupang hinirang, tuyag ka ng magiting, sa manlulupin, di ka pasisigil, sa dagatang tutok sa simoy at sa langit ng pagaw, ay hinatang tulakaw, isang paglayang minamahal, ang isang ng matawag mo'y tagumpay na nag-iindig, ang bituin at araw niya kailan ang ay magtitingin, luman ang araw ng walhagit pagsinta, buhay langit sa piling mo, ang inigaya ng pagkay mga amin, ang mamatay ng dahil sa'yo.
Hello and good morning, everyone. Welcome to this 9th episode of our webinar series for Fabfest 4. Good morning. I am your host for today. I'm Fidel Ricafranca. And we are very excited for this episode today because we have our very special guest, Mr. Santosh Nagaraju. But later on, we will have engineer Dioki Padaka of DfAM to properly introduce our guest speaker for today. So good morning, everyone. How are you? I hope you are feeling fine this auspicious Wednesday morning. And I hope to our friends there in Manila and Fab Labs, and especially in Northern Luzon, I hope you guys are safe and I hope you're doing well. So how's everyone doing? How are you guys? Can I see a virtual show of hands out there? I know you guys are feeling good this morning. Have you had breakfast already? Okay, so the Department of Trade and Industry, in partnership with DOST's Advanced Manufacturing Center, or AMCEN, celebrates Fabfest 4 this November 4 to November 27 with a theme Fabricating the New Normal. Fabfest 4 will have a series of webinars such as this one, leading up to the festival that will feature local and international experts who will discuss varied topics on innovation and design. This event will be brought to you live by Zoom and Facebook starting November 4th. Right now, it's the 18th of November, and we are on our 9th episode already. So I hope you guys have seen previous episodes. If you haven't yet, I believe DTI had them on their Facebook page. But for those of you who just want to catch up, we have um, we have three more remaining webinars. That's going to be on November 20th, also at 10 a.m. It's PCB 3D printing, bridging the gap for hardware engineers by Roy Perez. Also on November 23rd at 2 p.m., that's ASTM standards developed and additive manufacturing standards by Dr. Khalid Rafi and Dr. Alex Liu. Also on November 25 at 2 p.m., 3D printing high performance materials and industry 4.0 by Rigoberto C. Advincula. For today, November 18, our topic is going to be about design for additive manufacturing, or DfAM, now made easy with AM process simulation and generative design topology optimization by engineer Santosh Nagaraju. To introduce properly our speaker, may we call on engineer Dioki Padaka of DOST AMSEN.
Thank you, Fidel.
Morning, sir.
Morning. Additive manufacturing enables engineers to create parts that are not possible with traditional manufacturing techniques. As we watch AM progress from technology hype, one thing becomes very clear. Software will be integral to the success of the technology. Some of the greatest challenges in building metal parts with additive manufacturing includes distortion, residual stresses, and part quality. By replacing expensive physical trial and error processes with a holistic simulation approach, users can determine the optimal process flow much faster and at a dramatically lower cost. In today's webinar, you will gain insight on how to optimize design for additive manufacturing, or DfAM, using Apex Generative Design, and validation of new designs for metal 3D printing using SimuFact additive software. At the end of the session, you will gain knowledge on how to reduce significant time in topology optimization and manufacturing risks, as well as learn optimization techniques in the metal additive manufacturing process. Our featured speaker is a technical specialist for SimuFact engineering software, a business unit of MSC Software. He started his career at SFTC, a US-based material forming simulation company where he held various positions in technical support and business development. He also worked in the SKF bearing R&D team, taking care of forging, heat treatment, and rapid prototyping operations. He has a master's degree in machine design and has extensive work experience on material technology, conventional and additive manufacturing from the shop floor as well as on the CAE world. Since May 2018, he has been working with MSC Software as technical specialist for SimuFact, covering the Indo-Pacific region. So ladies and gentlemen, please join me in giving a warm welcome to Mr. Santosh Nagaraju.
Thank you, this is for the nice introduction. So before I start, I want to make sure my audio is clear for you guys.
Loud and clear, sir.
Okay, thanks. So, yeah, so let me share my screen. So I think you have to allow me to share or give me access to present.
Christian, can we have it set up, please? Thank you.
Yeah, I think you have to make me as a presenter so that I can put my screen. Yeah, now I can. Okay. and industrial development in terms of the major development in the polymers and metal AM. So then the greater advantage and the limitation to the additive manufacturing process. So then we look at in detail on how we can make use of software tools in the additive manufacturing process. It can be topology optimization, process simulation, or validating my design for the AM process. Also, we see like how AM can be used in re-engineering and reverse engineering process. So then we have a couple of case study, so which is already published. So you can even refer those in our website. So I picked few case study. So where we look on optimization, then how do we bring the new design? So it can be lattices, it can be self-supporting structure, or it can be anything which suits for the application. So then we look at one of the case where we optimized starting from studying the existing geometry, taking into topology optimization, then AM process simulation, and estimating the life of that 3D printed part. So that makes a complete 360-degree study of any component or a part which we want to replace with the conventional manufacturing process. So then we look at one of the lightweighting project we did for one of the passenger car. So then we can take up question and answer. So if you have any question, feel free to stop me at any point of time. I'm more comfortable with more interactive session. Or if you want to ask me a question, so just note it down and we can discuss at the end of the session.
Noted, sir. Thank you so much.
Yeah. So today industry, so we talk about the industrial revolution. So where we talk about different industries, like we talk about industry 4.0. So if you look at each industrial revolution starting from 1.0, so we have brought new technology to the industry. So 1.0 talks about introducing mechanism majorly for the cotton industry, where the human effort is replaced by mechanical gears and pulleys. So then 2.0 talks about introducing telephone and electricity, where the concept of batch production and mass production were brought into industry. 3.0 majorly talks about introducing computer and electronics, where we talk about more robots. So we talk about software. So when it comes to decision making, so it should be able to make the decision without manual interface. So when it comes to decision making, it should be able to take the decision with the past history or from the help of machine learning and artificial intelligence, so that it makes sure that the errors are automatically corrected. So if we look at major pillar, so why we are more focusing on additive manufacturing nowadays. So one of the major pillar for industry 4.0 is additive manufacturing. Also, we talk about other new technologies like edge or cloud computing, machine learning, artificial intelligence, advanced robotics, augmented reality, simulation, and wireless communication. So having said this, so today we will be majorly focusing on simulation tools, how the simulation tools will help us in making sure that we are in industry 4.0 and what is the development in additive manufacturing. So starting from design, optimization, process simulation, and replacing our conventional component with the additively manufactured part. So if we look at the market growth, so today we stand here somewhere 7.5 billion. So 3D printing compared to the conventional process, like it can be extrusion, stamping, casting, and molding process. So we are somewhere around 7.5 billions. If you look at 2030, the next 10 years, so it will be somewhere around 100 billion, where it will be growing at least 11x every year. So it is quite important to be part of this journey. The industries are slowly shifting towards 3D printing, and also we see other techniques like we talk about IoT, Internet of Things, digital twin, generative design, robotics. All are all are the new trends in the market where we are connecting real world into the digital world. So if you look at the generative design alone, in the sense of topology optimization, what we call it as. So even it is predicted at least 19% of growth every year, showing that the every engineer who is working on CAD will have topology optimization tool in his desk. All the design, whatever new design we create, it should pass through to the optimization tool so that we save time, we save material, so that all designs are optimized for the application. So considering all this, so it is quite important to be part of this journey, and we have to make sure so we will be we are more adapted to the new technology where the industry is going. So to understand, so if we look at history of 3D printing process, it is not something new we are inviting or adopting now. So it was there since 1970s where the first concept of 3D printing was laid out. So then the major development of material comes to the material development and machine development majorly started in 1980s. The first patent on 3D printing was filed in 1814. The major development when it comes to metal additive manufacturing processes started in 90s, where the new EAM process were developed, like a laser sintering DMLS process, the powder bed fusion. So on the new material. So as of now, major challenges, limitation in material grade. So those are still, we are working on that. So 2020 is quite important for the plastic, polymer and composites, because there are a lot of patent is going to expire in 2020 for the FDM process, like filament deposition method. So advantage here is the new player can come in, new technology, new material will come in, so that we will have more flexibility in adaptation, and market will see the new player coming into market, so that will be more easy to adapt. So if you look at the way of how it works, it's a layer by layer process where we spread each layer of powder. So if this picture shows with respect to the powder bed fusion, the each layer will be spread. So then we use either laser beam or electric beam. So if I'm using a laser beam, it is called SLM process. If I'm using electric beam instead of laser as a power source, then it is called as EBM, electric beam melting. So I will melt only the solid portion where I want to have my solid component. The major advantage here compared to the conventional process, in the conventional process, we always start with higher volume, then we subtract the material to get my final component. In the additive manufacturing, it's a layer by layer process where we utilize the material. So where we want to have the solid part. So rest remains as a powder. It can be reused with some filtration. So overall, so additive manufacturing is not something new. So it was there already in the market in the name of rapid prototyping, DDM process or layered manufacturing. So now it has gained more attention under the industry 4.0. So majorly the industries, it might be aerospace, defense or medical industry, are slowly adopting this technology because the logistics is not much. So if you have any CAD design, you can quickly get it printed. So now let's look at what are the different technology within that. So when I say 3D printing, it is not one technology. If I'm working on plastic and polymer, I have to go with the FDM, filament deposition method. If I am working with polymerization or wet polymerization material, so then I go with SLA and DLP. The major advantage between these two processes, FDM is quite faster and it is quite economic, but when it comes to the surface quality, SLA gives very good surface quality or surface control. So then we have SLS based on type of polymer I use. So if you are working on metal, then I can go with material jetting. So then we have binder jetting. So binder jetting again can be used for metal and ceramic. Then we have powder bed fusion, so where we have DMLS process, SLM and EBM. So we look at majorly the powder bed fusion here. in today talk, like how we can use this process majorly to address the challenges coming into the metal. Because plastic and polymer, so it is not expensive process compared to the metal. So we can correct the shrinkage, we can correct the warpage in FDM process with multiple printing or trial and error. But when it comes to metal, it is quite expensive because the each print is the material we use, the initial raw material and running cost is quite expensive. So that we have to reduce number of trials here when it comes to metal additive manufacturing process. So let's see further classification based on the type of material we use. So if you look at the classification based on material. So if you are working on polymer, so it is suggested to go with either SLS or FDM process. Again, it is dependent on what is the end part usage. Either you want to use it in just as a simple application or appearance, or you want to put it in as a thermal conductor, or based on the type of end application. So you can select what kind of process you can go. So broadly, we can say that if you're working on polymers, so you can go along with this technology. If you are working on metals, so then you can go with either DMLS or SLM process. So when it comes to metal, you can go with binder jetting technologies. So if you're working on sand, ceramic, so again, the binder jet will support sand, ceramic, and metal. So any kind of process, you can go with the binder jetting. So binder jetting is quite adaptable. So you can go with either of the material, and so initial setup is quite like it need quite large space. But when it comes to the other advantage, you can use multiple material compared to the DMLS process, and it has its own unique advantage compared to the rest of the process. So today, like we focus on powder bed fusion with the SLM process, selective laser melting. So if you look at the advantage and the limitation of additive manufacturing process, so we always say when I talk about additive manufacturing, the freedom to the design. So if you look at this design, so it is nearly impossible to manufacture with conventional way. So what we can do is if we have lattices and solids, so only way for us is 3D printing. So we are not only just creating the new design or fancy design. So we also make sure that whatever design we create or we print using 3D printing, so that is more stable. So also it is lightweighted, or more. Also along with lightweighting, it is more stiffer, and we make sure that it gives better life, making sure that stresses are equally distributed throughout the component, so that we increase the fatigue life or durability of that component. So then we talk about customization. So today we talk about a lot of customization in the fashion industry. So this is one example where we worked with folding bicycle. So based on the user requirement, so you can log into the website and you can define what kind of color of seat you want. So we can design using Digimat software. So we can design and develop own material which suits for the particular color. Also, we can take the passenger weight and we can optimize further based on the weight of the passenger. So coming to the metal or structural component, so we can use Apex Generative Design and further modify the bicycle. So based on the user demand, or develop a component for the customer. So this kind of customization can be quickly done, get it printed, have the design realization, and give it back to the customer with no time. So this is quite important, because when I say folding bicycle, it has to be always lightweight, because it will be either carried by the human, or we want to make sure that it is lightweight as well as it. So we fulfill all customer requirement. So not only that, so apart from that, we talk about speed to the market. So this is quite important, because if I fail to launch my component to the market within the specified time, I will lose that design to the competition, or I will lose the market to the competitor where he can put his component or design into the market. So it is quite important to be on time or reduce the logistics. So the greater advantage with 3D printing, whatever CAD model you have, you can quickly get it printed and have the design realization. So having said this, there are a lot of challenges. So one is limited material grade available. If I go with conventional way, so I have n number of material. So I can use any grade or I can use the lower grade to save the cost. So then I can go with the different grade of material, so which suits my application. So this is a challenge when it comes to additive manufacturing. So still we are developing or we are working on adding the new grades into the additive manufacturing process. When it comes to the initial investment and maintenance, when it comes to metal, it is quite expensive. When it comes to plastic and polymer, it is economic. But when I compare plastic and polymer, so we always compare plastic and polymer AM printing with casting or injection molding. So compared to the injection molding, so we are still not yet addressed the production issue and cost issue. So now still it is adopted by small and prototyping and medium scale industries. So not yet adopted for the large production when it comes to plastic polymers. Still the injection molding is a preferred one. So there are a lot of technique coming, a lot of machine coming where we can use that and use the plastic and polymer 3D printing process. When it comes to metal, so still we are competing with forged and casted component. So when it comes to the quality of part, so we always say 3D printed part is better than casted part, equal to the forged component. So adapted by the small and medium scale, not yet adapted or not yet approved in the large scale manufacturing industry. So we are seeing a lot of growth in terms of like recently HP has come up with binder jetting technique where they climb that 10x faster than DMLS process. Like that, we have a lot of new technology coming here, so where we can come out of this challenges. So let's look at DfMA in detail. Like when I say topology optimization or I'm designing for 3D printing process, so we always target for lightweighting. Then we want to make it the more efficient. So in terms of reducing the material, using the material in the proper way, so that I make sure that I use the more efficient way of manufacturing it and time to the market, so I can quickly optimize it and get it printed and validate the design. And the cost. So cost is an important factor when it comes to the industrial implementation, because we should have ROI for each and every component we manufacture. So these are the major focus. So I have to reduce my material so that I can save the cost. I have to reduce the material waste. Again, it will help me in saving the cost. And I have to be faster to the market. So I should have the quick design realization so that I can quickly go to the market and get more benefit out of it. So this is one example where we, this is one of the aerospace component where we reduce the weight by 63%. So not only just reduce the weight, so we can even reduce the number of fixation point. In this case, if we look at the initial design as multiple fixation point, then we reduce that fixation point to the 4 fixation point so that it can attach to the body or the surrounded component. Then we can have one integral design. In the sense, instead of having multiple small component, we make sure that we will have a single component which gives it delivers the design requirement. And overall time, so if you look at the overall time we spend for the optimization is just 2.5 hours. So in the lunch break, if I'm able to do the optimization and bring my geometry, then I can go for a further validation of design. So this is a greater advantage of MSc Apex Generative Design. So there are a lot of automation involved in this process, like meshing, geometry cleaning is automatically done by the software. So only engineer has to put his engineer thoughts in the sense of designing the stresses, boundary condition, and what kind of design output he want. So that rest of the meshing and geometry cleaning will be done by the software. So that we can have the quick design realization or CAD output, so which can be used for AM process validation. So if we look at the today AM optimization process or a topology optimization process, so we always start with creating the geometry in any CAD tool. Then we start with generating mesh for that. So then we define the boundary condition. Then it goes for optimization. Then we taken that optimized design for other software for meshing. Then it is taken to the one more software for the geometry cleaning. Then the verification will be done with the help of the third-party software. In this existing process, we use several different softwares, and there are chances that we may lose the data or information while transferring my data from one software to the another software, and it required a lot of human effort where I do the meshing and geometry correction. To be frank, meshing and geometry correction can be automized. It need not to be the human effort. It can be automized, and the software can do the meshing and geometry correction automatically. So better than what we do. So what we have done is we introduce optimization technique. So we MSc Software has acquired one of the German startup, which is called Amended. So then integrated to the MSc Apex. Amended was majorly working on automation of things in terms of meshing and automation. So now with MSc Apex Generative Design, you can either create the geometry or import the geometry and define your boundary condition and design goal. Rest of the meshing, geometry cleaning, and smoothing will be done automatically by the software, and it directly gives you the output in STL or CAD file format. It can be used for your third-party software or any software for the design validation. So there is no manual meshing. So user need not to spend a day of time in geometry cleaning, or you will not have any geometry related issue, or there will be no criticality when it comes to meshing. Software will do in the background meshing and geometry cleaning, and you can export that optimized shape directly to the STL or step file format. So this helps us in reducing at least 80% of time in the topology optimization. So let's look how it works. So it's a stress-based optimization tool, like we have many tools in the market. So it is purely works on the boundary condition it defines. So it applies the same set of load and understand where are the high stress and low stress. Where the stress is below the defined limit, it subtract the material. If stresses are higher than the defined limit, then it adds the material. So this is how the most of the stress-based optimization algorithm works. So then it works for the optimization. If you want to create a self supported structure like a tree root structure, or if you want to create lattices out of it, so we can define this as a design goal, so that it will help us in creating this respective design. So then controlling the resolution will be done automatically. The intelligent smoothing will be done automatically by the software. Also, it corrects the geometry. Majorly the smoothing the sharp edges and smoothing the area where we have critical cuts or lubrication holes or critical geometry, so that it generates the narrow geometry or a parasolid or a step geometry. It can be used for further application. So with this, we are almost reducing our topology optimization or generative design process by 80%. So majorly what we are doing, so we have added AM principle or automation in the background, so which takes care of the optimization process. Also, we have narrow AI algorithm, so which was more of artificial intelligence technique, but we call it as narrow AI because we are not going to the higher level of artificial intelligence. So we are using narrow AI algorithm where it studies the each and every design. So what is the percentage of change with the new design and old design doing topology optimization. And it compares with old design. If there is a 10% of, we can define even this. So if there is a 10% of change compared to the previous design, so then only it go for the next variant. So that lot of time in remeshing and defining the boundaries condition will be avoided. So that software will be much faster compared to the any software available in the market. Even with our own product, we have MSc Nastran. So compared to that, which is very much faster because we have added a lot of new algorithms into it. So greater advantage comes when it comes to the defining the thickness and minimum angle. For example, if I'm doing for, let's say, here, if I'm doing a optimization for additive manufacturing, so we should consider the AM principle during design stage itself. So that is the minimum thickness and the angle. So most of the, so when I say topology optimization, so it majorly focus on just weight reduction without considering what kind of manufacturing process I use. So when I say generative design, so generative design includes the manufacturability of that optimized design. So whatever weight reduction I do, so it should give the design which is more realistic for manufacturing. So otherwise I do the topology optimization, I reduce 90% of weight, my design look fancy, but I am not able to manufacture it because of I have reduced the material less than 1 mm, which is critical to print. If I'm using aluminum material with 3D printing, so if I optimize the part which is less than 1 mm, it is critical to print. So this is a manufacturing principle. And we should know all this manufacturing principle during design stage itself. So that while doing my optimization, I give my minimum thickness, I give my minimum angle, so that it will not optimize less than that. So that those features are only available in generative design, so that it optimizes and gives me the geometry which is more feasible for manufacturing. Either I am doing it for AM application or whether I am doing it for sheet metal forming, or it can be any kind of application. So here, if you look at the complete process here, so we load the geometry, define the boundary and condition. So then we define what is my design goal. In the sense, what is the maximum stress allowed? What are the design and non-design space fixation? So that rest of the parameter will be done automatically by the software. So this is a kind of geometry you get. So you can just right click and export into any software, or even you export into Simufact Additive for validation of 3D printing. So this is design for additive manufacturing. So if you look at, we always say, so 360-degree cycle. So most of the time we get the geometry, we define the boundary condition, and we will have optimized design candidate. So in terms of weight reduction or in terms of material saving. So this is just a 180-degree of optimization, but we don't want to stop here. So we have to start with our initial design, optimize for a AM process. Then you have multiple design candidate. In the sense, when you say topology optimization or generative design, so you will end up with multiple design or multiple iteration. You are not sure which design suits for your application unless you are validate for life, or you validate for manufacturability, or you check the design for durability. So if you want to complete the 360-degree cycle of design for additive manufacturing, we have to start with understanding the initial design, optimize it with the new material, or with the weight, optimize for weight reduction. So then you have multiple design candidate. So take this each iterate or each design. So take it to the Simufact Additive, validate for 3D printing, whether I can print this part successfully without any failure. So then take this 3D printed part along with the residual stresses and distortion, validate it for life or fatigue life of the component. So that this is my initial design and this is my optimized design. I'm making sure that my optimized design will withstand the same loading condition which was taken by the initial design, so that I am validating end to end without just ending my optimization cycle, just getting the weight reduction or optimized design. So we always suggest users, so go with the complete 360-degree optimization, so which include validation of design for life, manufacturability. Also, you can validate for the cost of each part. If you print multiple part at a same base plate, or if you print one part on the same base plate, you will have the cost, more benefit on the cost per part. So also you can play with printing the part with different orientation using Simufact additive. The first step, like optimization, will be done with Apex Generative Design, and the process validation will be done with Simufact additive. So this will help customer to validate their design, validation of design end to end with the CA tool. So once I validate for manufacturability and life, so now I can select one of the best design and go for my printing. So that since we have already validated, so it is easy to replace the conventional design with the 3D printed component. So in combination with the Apex Generative Design and additive manufacturing process. So this is one of the example where we used end-to-end application, starting from understanding the initial design. So if you look at here, so this is the initial design of a wheel hub for the race car. So we started with understanding the initial design. So then we used MSc Apex Generative Design to optimize the geometry. So then we taken that optimized geometry. When I say optimization, we end up with multiple design candidate. Unless we check it for life and manufacturability, we are not sure which design is good, or which design is critical for printing, and which design is critical for my application. So here we optimized it. So then we taken that optimized geometry for validation of manufacturability, in the sense 3D printing validation. So then we could able to manufacture whether I can print this part without any crack. So how best I can print this part. So then we taken this 3D printed component to add-ons, where we put the same boundary condition and loading, and we check for the durability of the component. So now we have end-to-end validation in the CA tool. So then we went for a printing of this part, and it is right at first time, and we could able to replace my conventional design with the 3D printed part. So this is a re-engineering process where we always start with understanding initial design, weight reduction or topology optimization, then validating for manufacturability and life. So if we talk about a reverse engineering process, so this we worked with one of the truck manufacturer. So where we wanted to have 10 gears, which is conventionally manufactured. So he wanted to have 10 more gears for R&D purpose. So he cannot develop a whole logistics, or he cannot develop a conventional manufacturing process to just get 10 number of gears. So what we have done is we've taken the existing design, which is of conventionally manufactured with the CNC and on the forge component. So we scanned this part, taken that scan geometry directly into Simufact. Simufact can read the cloud data or point data. So then we simulated, so which is the best way of printing with the best support structure controlling the distortion. So then we give this optimized process parameter directly to the machine. So with this, we could able to print this part successfully right at first time without not much trial and error. We could able to print, and we did the wire cut, and we could able to deliver the 10 component which is requested by one of the truck manufacturer. So with this, so the whole process was complete in just 3 weeks. We got the component from the customer. So we scanned it, taken into Simufact for the process optimization. Then we could able to print it, and we deliver it back. So when we kept both one to next or next to each other, so most of the people are difficult to identify which is 3D printed and which is conventionally manufactured. So greater advantage here. So if I want to go with conventional way, it takes at least 3 to 7 months. If I go with 3D printing, it can be done in just 3 to 4 weeks, not more than that. So that's a greater advantage when it comes to the reverse engineering application. So we do have a lot of case study in both re-engineering and reverse engineering. So you can refer to that with our in our website. So now the more important here. So how do we success in design for AM? So we always say these are the points which we should majorly focus. Like when I say optimization, we directly run into the software using the existing design. Like we try to apply lattices or honeycomb structure, but it's not really helpful. But most of the time, what we found is any new design has to be any design, or if you want to be successful in design, so we have to look for the new design idea based on the application. So lattices is not the solution for all designs. So we have to look at what is the existing boundary condition and loads coming over there. We have to understand in detail the stresses and apply the new design thoughts into that. So also we say a lot of automation tools are available now. So you need not to do the manual meshing or geometry cleaning. So make sure you use the new automation tool. Always add AM intelligence, in the sense if you're designing a part for additive manufacturing, make sure that AM principles are considered during topology optimization stage itself. While optimizing, so make sure that what kind of material you are using, if you're going with FDM or if you're going with metal. So as I already said, if you're going with aluminum 10 mg material, if you're optimizing below 1 mm, it is nearly impossible to manufacture using AM process. Those kind of AM thoughts or manufacturing thoughts should be applied during design for AM process. So if you miss this, or considering the minimum thickness and the angle, so anything which is less than 45 degree needs support. So if you optimize your design, considering the critical angle of 45 degree, you make sure that you reduce the surface area less than 45 degrees, so that you save a lot of support generation during 3D printing process, so that your design will be more realistic for AM process. And we always go with part level optimization. So don't overload yourself going with the system level optimization. Select one component for optimization and get that optimized and have that quick design realization. So then you can go for a system level optimization. Always make sure that resources are available in terms of material, in terms of machine, and in terms of manufacturability. It can be the cost. So if you're optimizing the component and if you want to 3D print, so don't go with a very simple design. So if you select a simple design, which is easy to manufacture conventional way, it makes no sense to adopt AM technique. So whatever design you select, it should be critical, or it should be challenged to manufacture in conventional way, so that we can manufacture in additive manufacturing. The greater advantage of additive manufacturing, we can print the complex design, so that you have to always select your initial design, which is difficult for conventional manufacturing, so that you will have a better justification when it comes to cost and design or manufacturing design. So then you can apply the innovation, so we can quickly get it the new design or optimized design. So always it is critical to justify by the cost, otherwise it is always rejected by the design team because of either cost or easy of manufacturability. So when I say AM, so there is no challenge of easy of manufacturability. Any complicated shape can be printed with AM. So that's quite important. So we had to come up with the new ideas, not taking the age design thinking. So we can use the new tools, automation tools like Apex Generative Design and Simufact and Adams, so that we can validate our optimized design end to end, including manufacturability and life. So, and we have to include manufacturing principle during design stage itself, so that it will not be rejected at the end of design. And we have to use the new techniques, so that we use the new optimization technique. It can be self-supported structure lattices, and we have to make sure that we will give the cost benefit so that it can be adopted for the productions. So now going into the few case studies. So I selected a few case studies so where I can explain how the optimization was done, then how do we reduce the weight. So there are a couple of case studies of which you can refer to our website. So this on a race car. So this on passenger car where we have done weighting of a light hinge component. So this on medical implant. We worked with one of the hospital here to support tumor patient. So then there are a lot of case study available in our website on aerospace, defense, and other applications. So we look at majorly the first two case study in detail, along with a couple of case study on light weighting. So this is one of the satellite launcher where we worked with optimization of it. We always start with understanding conventional design. So what is design and non-design space? What are the loads coming over here? So then we go with the optimization of the geometry. So in this case, so with optimization, so we could able to bring weight reduction of 55%. So same time, so we are not only majorly focusing on weight reduction, we make sure that the component is more stiffer, and also we make sure that we cannot make stress zero. So we always make sure stresses are equally distributed so that I can play around and increase my life of the component. So there's one example where the satellite launcher was optimized. Previously, it was cracking after launching some of the satellite here. So it was cracking at here. So we given some extra coating here. So after that, we thought, why can't we optimize in such a way that stresses are equally distributed and we will have better life of the component. So it is optimized and 3D printed. So it gives us a better life compared to the conventional design. So this with the G bracket challenge. So we always say, when you say topology optimization, so you end up with one design. So with MSc Apex Generative Design, based on the end application. So you might be optimizing for structural application. You might be optimizing for acoustic or 3D printing. So based on the end application, I can get my design candidate which suits for that. If I'm doing a structural application, so I cannot go with lattices because the multiple dynamics of loading coming over here. So I have to have a more stud design or more thicker or stiffer design when I go for the structural application. If I'm going for a acoustic, I don't want to change the surface level because I'm more playing with acoustic. So then I can keep the same surface and just optimize the thickness. When going with AM, then I can have the different design candidate. So this kind of design with the same set of boundary condition, based on the application, we can have the different kind of design candidates. So that's quite unique because if you go with Nastron or any other tools available in the market, irrespective of what kind of application you are using, you will have just one design output, whether you are using for structural, aero, or 3D printing application. So Simofact, along with Apex Generative Design and Simofact Additive, you can have different design candidate, get validate for 3D printing, and you can even validate for life, so that you are not only creating a new design, you are validating for life and manufacturability, so that you can justify your design optimization. So when I say optimization, so we always run with or we driven by the software. So when I say optimization, most of the engineer run into the desk and try to use the existing tools available in the instead of applying its own design. So this is the example. Yeah, thanks. So these are the example we inspired by the nature, like So when I say optimization, so there are a lot of ideas is available around us. So the example, so if we look at Japan bullet train, so which was making a noise when it is passing through the tunnel, it was inspired by the Kingfisher. Then it was designed in such a way that the noise is reduced by inspiring by the Kingfisher, what we call the Kingfisher knot. So then when we talk about optimization of aeroplane wing, so they have adapted this eagle wing in the aeroplane wing, so which helped us to improve the efficiency by 5%. So this we always say, don't limit your thinking by the software. Try to get the new design. So then use the software to apply those design. So we had same approach. So where we got this self-supported tree structure from from one of the engineers. So we thought, why can't we use this self-supporting tree root structure for one of the trophy, so that we optimize this base with the self-supported. So when I use this kind of a structure, you need not to provide supports. There no need of generating support during 3D printing process. Then we adopted lattices plus solid and self-supported. So we could so with this we could able to reduce the weight, as well as we created authentic design. So then we could able to print this part without any support. So we printed this part without any support. So this is the kind of ideas we get it from the nature. So don't always restrict yourselves for the software. Get the new idea from outside and try to use the software to validate those designs. So this is one of the best example for that. So there are a lot of example like optimize the drones and biocompatible lattices and more on structural components. So all this optimization was done in Apex Generative Design and validated with Simofact Additive. So I will not spend much time on this because I already left with 5 more minutes for Q&A. So just to take a few more minutes on explaining end-to-end. So this is one of the race car example. So when I say race car, it is quite critical when it comes to loads coming to the wheel hub. So also 1% of weight reduction is increase my speed of the car. Also it makes my car is more fuel efficient. So we started with initial design. So then we understand the loads coming over there with MSA Adams. Then we selected the design and non-design space. Then we got the different design candidate. We validated for manufacturability. Then we validated for life. We could able to print and CT scan. Then we could able to replace existing design. So how do we start it? First, we understand the initial design and critical loading to define the design and non-design space. Then we optimized it using Apex Generative Design. Then each design is validated for manufacturability, and we estimated the cost and life of it. So with Simofact Additive, we check the manufacturability. We make sure that no cracks during printing and it can be able to print without any manufacturing risk. Then we taken back all the studies, how much support we need if I print each part. Then we could taken that manufacturing residual stresses. We replaced the initial design with the optimized one, and we validated for the durability or fatigue life of it. So with this, we could able to technically evaluate as well as we evaluated commercially. So calculating cost for it. So then we could able to select one design, which is technically qualified as well as commercially qualified. So any new design, so most of the time we pass through this all phases. First, we technically evaluate, can the design withstand the load? Can I manufacture it? Then I go for calculating cost for each component. If I print one part or multiple part, how much cost I can reduce? Then I can select one of the best design for the manufacturing. So this is a design where we could able to print and put it back into here. So this is running quite successfully from last 1.5 years. So we have a lot of cases like this where we digitally or virtually validated the design. then we could able to print and replace the conventional with the additive, the manufactured part. So this with lightweighting of the component, we selected one of the 316L component, the conventionally forged and sheet metal component. We could able to optimize it. So with optimize, we could able to reduce the weight by 70%. Also, we reduced a lot of integral part like nut and bolts. So that reduced the more assembly component. So then we structurally validated for the life of it, the structural life of it. So then we provide end-to-end solution saying that, so starting from design, optimization and testing. I will not spend much time here. So with this, so we have a lot of e-learning training and software licensing options. So if you want to understand more in detail, so you can visit our website. So just to give a background, so we have solution for material development. We have solution for a topology optimization. We have solution for 3D printing. It can be a metal, polymer, plastic, and we have different solvers. If you want to validate for life, you can use the Nastron, and we have different solver together. So basically, MSc software started with Nastron, NASA Structural Code for Space Application. So then it is acquired a different solver in the different physics, because same physics cannot be applied for different application. If you are working in material, so then you need a different equations. So then we have categorized different tools based on the application usage. So that if you have working in any of this field like material development, optimization, manufacturing, assembly, or validating or system level optimization. So we have tools for that based on your application. So not only we focus on 3D printing, so we are also focusing on other techniques like direct energy deposition and metal binder jetting. So metal binder jetting greater advantage. So there is no support required and it can address the large scale production issue. There are a lot of development happening in the current industry in terms of DMLS process, printing process, the DED, repair process, and metal binder jetting for the automobile applications. So with this, I request you to visit website for the more details on the product and for the case study and e-learning. So also we conduct regular webinars. So last time it was virtual webinar. So also we conduct a lot of training material. We have training material from one of the subject matter expert. You can register for even the virtual webinars going on the current series, like November series on this. So with this, so I end my presentation. Thank you very much for your time. So now time for question and answer.
Thank you so much, Mr. Santosh Nagaraju. That was very enlightening, especially for us. I personally am a big fan of generative design. And I know most of you here, especially in the chat box right now, is very excited for generative design in general. I just have a couple of questions, or before, maybe someone can, if you guys have questions, maybe right now is the right time to raise them up. Okay. So, but if you don't have one, let me just start with a couple of questions. I think the most obvious concern right now, especially if you try to minimize the amount of material that you add into the manufacturing, would be about the durability of the final product compared to the fully printed output. Is that a valid concern for us, especially it's, you mentioned it's like 80% more efficient?
Yeah, so general rule. So from our experience, what we always say is like when we say topology optimization, as I said, we always try to focus on only material reducing. So that is not our end goal. So we have to make sure that component is much stiffer. It gives equivalent or better life compared to the conventional design. So it is always better to start with understanding the initial loadings, loadings and boundary condition, then study the material availability, because when I say 3D printed part, it will not have equivalent strength with conventionally manufactured component. So if you're comparing with the casting component, so 3D printed part is much better. It will have better strength. When you are comparing with the forged component, so it will have 80 to 90% are based on what kind of parameter we use. So it is always equal. We cannot say it is always better than that. So it is quite critical. So when we go to the topology optimization, so please do focus more on life and durability point of view, majorly the fatigue life point of view. So not not only focusing on the weight reduction. That is better. It will have better strength. When you are comparing with the forged component, so it will have always, I always say, don't go with a very simple design. So go with a design which is critical for conventionally manufactured, so that you can justify. Otherwise, which will cost 10 USD with the conventional manufacturing. If I go with the AM process, it may cost 200 USD. It makes no sense, or I cannot justify my management saying that why they have to go with additive manufacturing. So go with the design which is critical for conventional manufacturing. So apply lattices, apply your own ideas, so that it can be done only through AM, so that we can have better justification why we need a additive manufactured or optimized shape for that particular application. So that is the best way to start. Yeah.
Thank you. Thank you so much for clarifying that out. Christian, I will just share my screen real quick. Because personally, I've also seen
my. I posted my email address. If you have any question, so feel free to write me.
Right there. Thank you so much, Engineer Santosh.
I'm always here to help. Yeah.
Okay. I've seen this very interesting project way back in 2007 by designer Joris Larman. It's called the Bone Chair. I'll just quickly share screen one that I have right now. I think this is what encapsulates generative design, really, no?
Okay.
Yeah, I believe these are, fundamentally, this is what the promise of generative design is, where you provide a specific set of restrictions or a specific constraints, but also a general idea of what the chair you're trying to, the thing that you're trying to accomplish, which is a chair, and then the software does it for you. Is that about right? I think the bigger question right now is what software is available right now to do this?
Yeah, if you look at the market, there are n number of optimization tools available in the market. So one is Apex Generative Design. So why I call it as generative design? So when I say generative design, so you can give manufacturing constraint during the optimization stage itself. So that is very critical. So if I only focus on weight reduction, I can create a very fancy design. But when it comes to manufacturing or estimating life, it will fail. Most of the time it will fail because I have not considered my loadings. I have not considered my manufacturing method. So just I try to reduce the weight and try to get the fancy design. That is not always realistic. So I suggest go with Nastron Solo 200, so which is very much proven, or go with Apex Generative Design. So that you start with optimizing it for the application. So then take this optimized shape. So before you go for manufacturing or concluding your design, so take it for a structural software. It can be Apex or Nastron. Put the same boundary condition, apply the same loads, and validate it for a life. So not only very basic static loading, apply the dynamic loading and apply for the fatigue life of that optimized shape. So that you are optimizing it as well as you are validating it for the life. So that then you can go for a manufacturing. I think if you can go with this steps, do the design optimization, make sure materials are available. So then validate it for life, considering the durability, stress, and boundary conditions. So then I think we see success in DfAM. So we should not just conclude without validating for life. So I think we have a lot of cases where we worked end to end, starting from optimization. Yes. In fact, we failed many times, and not like we got the success in first iteration itself. When we put it for a stress validation, it failed because we cannot have very critical or very thin section where we have more stresses or where we have fixation points. So we always suggest start with the optimization tool, life validation, then we validate for manufacturability or get it printed or prototype. So this process should give us a very good optimization of any design which you select.
You've mentioned earlier now we should in a way that we should take this with a grain of salt. Like the approach in general is promising, but the durability and the general structure is not a foolproof method to do anything. What do you think is a proper approach when it comes to manufacturing this? Does casting and does casting still play a vital role in, like, say, if one tries to make this into the market, like in a more mass-produced manner? I think casting is still a process along the way for these kinds of design.
True. When it comes to the dimensional control, like if I talk about 3D printing, so still we have limitation in the space. So whatever design you showed, like chair, it can. I'm not sure it can be done with 3D printing because if you look at the logistics,
it's too big for the curve.
Maximum 400 into 400 dimension. Mm-hmm. So we have to go with either any other technique which is available. So if I go with plastic and polymer, so there are some other approach, like I can go with the FDM with a larger base plate.
Larger bases, yeah.
So that can help us. But coming on to the material grade, so again it is a question, like
definitely
the material grades we are using for AM, whether that is certified or have we tested that for the applications.
The ones you've tested, this powder bed fusion method, in general, what type of metals are these?
So we have different grade. If you talk about material, you have a margin steel grade, you have aluminum, then you have Inconel, which is used in aerospace. Then you have titanium 64, which is qualified for aerospace, as well as you have titanium 64 ELI, which is certified for medical application. So medical application is quite critical because the part you manufactured, it goes inside your body. It should not react with your blood. Mm-hmm. That should not cause any further disease instead of curing existing disease.
Definitely,
there are only a few. If I can name, I know only TI64 ELI, which is certified for medical application. So like that, we have a limited material grade. That is one of the challenge when it comes to metal. So we have to make sure if I'm selecting 316L of forged component, I should have equivalent grade in 3D printing also, so that I can replace the conventional with 3D printed one. So
is the type of laser? Sorry, is the type of laser also critical in during the binding process of these?
Yeah. So when it comes to power source, it can be either laser or electric beam.
Okay.
So again, we can further classify, like if I'm printing a turbine blade, so sometimes it's recommended to go with EBM. So EBM is quite faster, electric beam melting, because I can go with the larger layer thickness. I can use the more energy source. So it is much or at least 2 to 10x faster compared to the laser or SLM process. So again, coming on to the application based, so now we have a binder jetting option. So metal binder jetting. So binder jetting was only available for non-metal. Now you have new machine coming, which can be adapted for metal also. So that doesn't need any support, and you can print part very quickly compared to the powder bed fusion. So that also helps us when parts are not critical. So again, it depend on what is the end application. When you are not using for rotating component application, if you're using for just a static loading or structural application, so you can go with metal binder jetting.
Because
So
when
that,
the moment it starts to get applied in any rotating functions, it totally changes, right? Like, you know, the concerns are definitely changed.
Exactly. So why we say that when I say metal binder jetting, we use gluing material, which is not stable at higher temperature. My end application is engine application or exhaust system. If I put metal binder jetting component, it is the property of glue will change based on temperature.
It might disintegrate, right?
Exactly. So I have limitation in my temperature. If it is for structural application, yes, it suits for that. So this is a kind of study we have to get before we select any kind of a process, whether I go with SLM, EBM, or FTM, or metal binder jetting.
So yeah, in your process earlier, you showed us a cog, or that gear that you 3D scanned, and then you sort of reverse engineered, and then you manufactured. I believe that was also done in, or rather applied for a circular motion, right? Well, I'd like to know how it went. I mean,
yeah. So when we got that project, so we had an initial discussion with one of the truck manufacturers. So we know that it's a rotating component, and we have a frozen type of manufacturing process because it's a gear component. There are critical loads coming over there. So we want to go with metal powder bed fusion only with the SLM process. So we frozen what kind of manufacturing process. So then we selected the one of the proven machine. So for the printing, so challenge was like when we have the conventional part, so we have to deliver the same strength, quality, and we have to make sure that we can print without any defect. It should not be any cracks. It should not be any surface layer related quality in terms of RA, surface roughness. So what we did is we scanned the geometry with hexagon scanner. So you can use any scanner, blue light or red light scanner. Get that scan geometry directly into the SimuFact so that you can optimize in terms of what is the laser power you use while doing a 3D printing. So what is the best support structure? If you can further optimize, like instead of printing one part, if you can print two parts, again you will have cost benefit. So if you can print two parts on the same base plate or three part oriented in a different way, so then you will have further cost optimization in the process. So all this study is done with the help of SimuFact Additive, so that when we have end-to-end process validation for the life, for the manufacturability, so we can be right at first time. So there is no physical trial and error process. You validated the design, so now you can go with right at first time. You get it printed and deliver back it to the customer.
I can only imagine the initial labor pains that you had to go through. I mean, like the learning curve for you to get the parameters right for this one, right?
True. So there are a lot of hints. So it's not always true. We printed right at first time. We printed a small coupon with some material, because when I change the material supplier, so again based on the material supplier or batch, even though it is the same grade, there is some changes in material behavior. So we always try to validate that printing the small coupon on the same machine, understand whether it will behave the same. So measuring the strains or distortion, so measuring and comparing with our standards. Okay, so it is within the design spec, so that I can qualify this batch of material for the printing. So we go with a lot of small, like we say it as a milestone. So we optimize and validate using CAA tool. So that is my first milestone. Then I go for physical printing. Then I print a small coupon and validate. That is my second milestone. So then I go for actual printing of the component. So once
you've mentioned there are still layer, those concerns in between layers, or is that still prominent in powder-based na printing? Because it is mostly in FDM type na printing with like PLA or ABS or most of those thermoplastics.
Yeah.
Do you still have those concerns in?
Yes. So if you talk about a PLA or a FDM process, so when it comes to FDM process, we majorly look for shrinkage.
Mm-hmm.
We majorly look for the kind of a delamination we get while printing.
Mm-hmm.
So what we do for that is we can run a couple of examples. So you take the optimized design and you run the process in DGMAT and you observe the shrinkage, because you cannot make shrinkage zero. It is a material behavior or it's a material science. Then you change your initial design based on the shrinkage. If you're feeling shrinkage, let's say you predicted a shrinkage of 1.2 mm in X direction.
Mm-hmm.
You change your initial design in plus X, or we call it as pre-compensative or geometry.
You have to do offsets with your
exactly.
Mm-hmm.
So then go for printing, so that you need not to spend much time on the process. So if you try to work on shrinkage and warpage, it takes very long time.
Mm-hmm.
So better to go with your optimizing initial design. So allow part to shrink because it's a material behavior. If I try to constrain that shrinkage, what it does is it generates a lot of stresses within it.
Yeah.
I should allow part to shrink or deform. So then only it will release the stress and part will be free of residual stresses. I put more constraint in terms of support or printing in different directions. So I should not constrain the part to expand, or I should allow part to show thermal behavior in terms of expansion. I should allow part to shrink to release the mechanical stresses, so that my final part will be free of any defect.
Also, that way you will have a better control on your final output, right?
Exactly. So you design in such a way that once you optimize, you simulate for manufacturability using FDM technique or SLA technique, understand the shrinkage and behavior, change your initial design, allow part to shrink or release the stresses in terms of thermal expansion, so that you will have the very clear or good component which is of less residual stresses, and it gives you the better life. So that can be used with tools like DGMAT if you're working on a plastic and polymer field. If you're working on metal, then go with Simufact Additive.
Well, right. Thank you so much for that one, Mr. Santosh. Let us check our chat box real quick for some questions from our participants. We have a question from Mr. Marie Gallego Jr. What is the percent of material wastes using this method of technology? I understand he might be coming from thermoplastic printing. So understandably, there are like a lot of wastes in the process. In this method that we are having right now, powder printing, are there specific are there important aspects that we need to understand when it comes to wastage?
Okay, so let's categorize into two. One is on metal and one is on plastic and polymer. So when we talk about plastic and polymer, so based on the application, the major material waste is a support.
Definitely the support
which you are generating is going to be material waste. But there are processes where you can again reuse that support material.
So if you talk complicated
about, yeah, so it can be used for only the R&D purpose, not for the regular
yeah.
Because the reused material may not give a good
compromise.
So when it comes to metal powder, so metal powder, again, whole chamber is filled with a layer, so you will only melt the area where you want a solid part. So there are at least 5 to 7% of material waste again in the metal powder bed fusion, because the part which you print, the area surrounding to the powder surrounded by the part printing will undergo the thermal cycle. So it may not be suit or it may not be reused for the regular application, because we have to compromise on the material property. But in general, we say 5 to 7%, not more than that. Again, the support printed is a material waste. So that's why we always say try to minimize the support. So also from the thermal point of view, so higher the support, you are giving more heat to the system, so that your residual stresses will go up. So you orient the part in such a way, so you reduce the support structure. So you orient in such a way your surfaces are not less than 45 degrees, so that you avoid the support structure. Or take that critical angle during design stage itself, so that you are much taken care of design constraint during topology optimization itself. But yes, there is at least 5 to 7% material wastage. So it is very much compared to the conventional process, it's very much better, or we say very few or very less material wastage in the additive manufacturing process. If I go with conventional way, at least I have 60% material wastage. So in EAM, we can say 5 to 7%, not more than that.
Because I think the biggest promise of powder bed printing is that the powder itself acts as a support structure while it's printing, right?
True. Also, it acts as the insulator.
Yeah. I think really that's also, especially with metals. I haven't seen that side of printing yet. Where the powder acts as an insulator. Thank you so much for that one. I just have a couple more questions before we wrap up. In general, additive manufacturing has been there for like decades now. Do you think there's definitely a future where we can break in, or rather break out beyond the niche manufacturing and the hobbyist level, 3D printing parts and so on? Can we is there a few does the future is there a room for us in the future to actually break into the mainstream manufacturing, so to speak?
True. So in one of the slides, I presented it is not additive manufacturing is not something
where
they're already from 19.
The powder acts as an insulator.
But if you look at the technology and the trends from 90s, so we have seen the new materials coming into market, the new machines coming into market. The major challenge is printing time. So if we talk about current challenges, it takes days of time to print a component, and I can print only 1 or 2 components at a time. So these are the major breakthrough we have to come out. So to give you a couple of updates. So if you look at the new technology from HP machine, which they climb, which is 50x faster. So what we need to break out this challenges to make sure that industry will adapt to this AM process. So we should have more material grade, which can replace the conventional grades. And we should make sure that the AM parts are more economic. So now that is quite a challenge, because if you look at 10 years back, when I say AM, it was just a prototyping technique. It was not even adopted for the small and medium scale. Now you slowly see the small scale industries are already, or you see a lot of service bureau, which
it's in kitchens,
they're already available for 3D
schools.
Yeah,
it's practically everywhere.
Exactly. So now it is slowly the AM is coming into the market. So now it is majorly focusing on the service bureau. And also I see a lot of news in the AM industry portal, like the many industry, like aerospace industry, they target at least to replace 20 to 30% of the part by AM part, like 3D printed part, like major aero industry. So also I see a lot of application in marine. or critical application. So if someone is working in a ship, so he or even in the army, so they cannot have a one part. So for example, part fails in the army or in the oil and gas industry, so they cannot order a part from the land. It takes 3 months to ship and reach to the oil and gas factory. So what they are trying to do is
manufacture
now,
on site. Yeah.
yeah, so they are trying to have their own 3D printed machine within their premises. So if some part fails, so they can quickly print it and replace it. So even I have seen a lot of publication where they have already adopted it. When it comes to the logistic time, so if part fails, they cannot wait for a 6 month of a logistic cycle. So they are quite okay to get it printed with no time, and they want to fulfill or they don't want the production to stop. In those critical area, I have already seen AM is already adapted. So coming to the
definitely, yeah.
Automobile. So automobile, where we talk about millions of parts. So that is a challenge or constraint for AM. So we are not yet there where we can give million or we can print millions of parts in a month. So that is the one hurdles we have, but I see the binder jetting. I think that can help industry to adapt. But for sure, there are a lot of adaptation coming. So already in ISRO, Indian Space Research Organization has already launched a satellite which is consisting of 3D printed nozzle. So it is already in the space orbiter. It's working fine.
Do they 3D print in the International Space Station already?
Yeah. So we see a lot of good cases because at the end we need a case which justifies or which is a proven case. So space organization, there are a lot of component which is already flying. There are a lot of component. One is which I showed, light hinge. It is already there in many passenger car.
Oh, okay.
Passenger car, at least we have 5% of parts which is 3D printed. Coming onto the two-wheeler motorcycle, so we have a lot of fancy designs. Even in the Mini Cooper, I have seen a recent video where they have 3D printed or customized design, majorly the jewelry. So it is already adapted by 3D printing. The medical implant. If we have a patient who is with the cancer, I cannot wait 3 months to get a small part printed with conventional way. So I can get it printed in 3 weeks and put it into the body where I want. Also, it is challenge when I say kind of a tumor or cancer. It's a growing disease. So most of the implants printed for a tumor. So nowadays I see 60% are 3D printed. This is a huge achievement of AM because now it is also quite challenge for conventional way. So cancer is a kind of a growing disease. If I wait for a month, your complete design will change. So what you ordered and what you get is completely different. So it may not fit for a patient. So we worked with one of the hospital here in India. So they put a very tight timeline saying that we need this component within just 2 weeks. So it is with the titanium ELI material. So we could able to validate and print and given back to them so that they should, whatever design we give, it will fit perfectly into patient. So otherwise, each time we do the reiteration because it's a growing cancer, we have to design based on the current condition of the patient. I cannot refer to my old design. In that condition, I think AM is the only solution I can say. So there is no other alternate, or it is already proven like 80% or so 60%. The major implant provider also said that they are focusing at least to replace 80% of the component by 3D printed one, majorly focusing on the tumor application. So that is a great news for AM.
Yeah, I think that's a very great news for everyone out there, not just for us makers, but for especially for the health sector, for the new generation of learners and educators as well. Thank you so much for shedding light to that experience of yours and all your insights that you've gathered all these years you've been working in additive manufacturing, Engineer Santosh. I guess we can wrap up now. Everyone, if you have questions, for those of you who are watching this on Facebook Live, and for those of you who are just about to watch it on the comforts of your home, you may email Engineer Santosh over at santosh.nagaraju@hexagon.com. Yeah. Engineer, would you like to add some final statements? A couple of promotions for your software or for your company?
Yeah, from my end, first, I would like to thank you for inviting me and giving an opportunity to speak. The second, on the software point of view, I don't want to just talk on the particular software. In general, so we always say there are a lot of technique available, so a lot of CA tools available, so which makes easy for engineer to certify or validate its design. So make use of those tools. It can be MSc tools or any CA tools available in the market. So that whole process or whole design can be validated end to end, starting from design, manufacturing, and life. So make sure that you spend very less time and trial and error and make use of the new or the artificial intelligence techniques, CA tools. Make use of the technology available, I can say. So with that, I know that already you are familiar working with the TGMAT, Simofact Additive, and Apex Generative Design. So we are also working very hard to bring new technology in terms of whatever technology coming, like binder jetting. We want to help engineer make sure that the technology is easily adopted. So with the low cost. So because cost is the barrier, so we should allow engineers to experience the technology. It might be in terms of generating new design. It might be in terms of 3D printing. So everyone cannot offer a metal 3D printing machine. So that at least with the CA tool, you can have the experience, like if I print a particular design using 3D printing, how it looks, what are the challenges you get, so that you can have the basic idea. So before you go for actual printing. So in that way, we are putting our best effort to make sure or educate all engineers in terms of feeling the new technology available in the market. And we are always open if you need any new development. So we are okay to collaborate because we are more from the developer side. So we want engineering mind to tell us what they need so that we can develop and deliver to them. Yeah, so we are here to help in terms of technology and FEA point of view. So,
awesome.
Thanks.
Thank you so much. Thank you so much, Engineer Santosh. That was a very enlightening discussion from you. And for those of you who are in the Philippines right now, kindly take note that our program sponsor, AMSEN and DOST, they give you this opportunity to actually learn these machines and not just hear it from the internet. They have their AMSEN facility right over at the gig. Make sure to reach out to your DOST AMSEN representatives. I think Engineer Dioki Padaka is right here with us right now. But yeah, for those of you who are asking in the chat box regarding the certificates, kindly reach out to our DTI hosts. If you have no more questions, let me just fill you in with the Pavsik Laban. Sorry for the roosters back right here in my background. They're having the time of their lives. But yeah, ever since we had our Fabfest 1 back in 2016, DTI has always been supportive of the makers and the small and medium enterprises in the Philippines. And every Fabfest, we would have a show and tell, some sort. For this Fabfest 4, since we are limited with our mobility, DTI is actually asking everyone from Fab Lab in Ilocos to Fab Lab in Davao and down there in Mindanao, if you guys have interesting adventures so far in during the pandemic may be helping out your local hospitals or your local frontliners. The Department of Trade and Industry, in partnership with UST's Advanced Manufacturing Center or AMCEN, we would like to invite you for this year's Fab Siklaban 2020 competition as its flagship event for this Fabfest 4. So Fab Siklaban 2020 is open to recognized Fab Labs in the Philippines and will be showcased in 2 categories. So first category would be the COVID response innovations, and the second one would be Fab Lab innovations in general. So in this connection, we are excited to invite the Fab Labs in your area or region to join the competition and share to the rest of the world your authentic creativity and innovativeness. So Fab Siklaban 2020 mechanics and criteria are shown below for your preferences, or you may ask DTI for a copy of this one. But prizes for each category are as follows. First prize is 10,000 pesos worth of gift certificates plus a certificate of recognition. Second prize would be 7,000 pesos worth of gift certificates plus certificate of recognition. The third prize will be 5,000 pesos worth of gift certificates. The deadline of submissions of entries is on November 23rd at exactly 5 p.m. And awarding of winners will be done live via Zoom and Facebook on 26th to 27th of November 2020. That's next week. So your deadline is next week, Wednesday at 5 p.m. And our announcement of winners will be on the 26th and the 27th. That's the Thursday and Friday next week, respectively. Okay. So, moreover, Fab Labs in the Philippines will be featured during the 3-day event. So, in line with this, we enjoin you to submit your 3 to 5 minute promotional video of your Fab Labs on or before the 23rd of November at 5 p.m. So, guys, I know you've been working with those videos over a couple of years that you've started your operations. So now's the right time to showcase them and, let the rest of the world see it, especially those who haven't joined our Fab Fests in the previous years yet. So for all your types of submissions, may it be for the contest or just for the showcase, kindly contact Miss Marilyn C. Tansinko of DTI 7. Her email is marilyntansinko@dti.gov.ph. I'll repeat that once again, marilyntansinko@dti.gov.ph. DTI Cebu or DTI Region 7 will post official details on the contest mechanics over at their Facebook page, so just kindly follow them and check for future updates. This has been a very enlightening moment for us. Thank you so much, Engineer Santos. Thank you so much, Engineer Dioki Padaka, for introducing our guest speaker for this morning. For this Friday rather, sorry. Make sure to stay tuned for PCB 3D printing, bridging the gap for hardware engineers. And then we have a free webinar again by Roy Perez, an electrical engineer by training and an applications specialist at Volterra, working alongside engineers from small scaling startups to Fortune 500 companies like Microsoft, Apple, and Google. So let's invite our friends, our electronic and our ECE friends. Excuse me, who's doing this thing? To join us in this another promising talk by one of our fellow Filipino engineers. Okay, so if you have no more questions, this has been Fidel. I'm part of Fab Lab UP Cebu. I'm a resident maker. At the same time, I'm also Fab Lab manager. So if you guys have questions for Fab Lab UP Cebu, me together with Miss Mona Alcudia, we will entertain your questions You may email us over at fablab.upcebu@up.edu.ph, and we will be more than willing to help you out on your design ideas. Okay, so from Cebu, from all of us here in Cebu to the rest of the world, thank you so much for joining us in this morning's activity. Thank you so much again, Engineer Santosh and Engineer
Thank you so much,
Yogi.
Second.
You guys have a great day and see you again on Friday. Thank you so much. Bye bye.
Thanks and have a great day. Bye.
Thank you.